Welcome to the video lesson for section 4.3, Trig Properties. Today we're going to look at some properties using our sine, cosine, and tangent functions. We're going to use them with some equations and some expressions to simplify, and we're also going to use them to solve some triangles. Let's get started. All right, we're going to start off with our reciprocal identities. To begin with, we talked about the fact that the sine and the cosecant are reciprocals. Here we're going to kind of highlight that again. Looking at a reference angle of A down here at the bottom left, we can see the sine is the opposite side over the hypotenuse, stated over here with a ratio. And since the cosecant is a reciprocal, it's going to be the hypotenuse over the opposite, which leads us to our two reciprocal properties. The cosecant is equal to 1 over the sine, whereas the sine is equal to 1 over the cosecant. And the way you'll see us using this is to help us rewrite expressions to kind of simplify things as we're walking through some trig proofs. We can see the same thing is true for our cosine and our secant. Again, they are reciprocals. So whereas the cosine is going to be the adjacent over the hypotenuse, the secant would be the hypotenuse over the adjacent, which would lead us to our two reciprocal identities for the cosine and the secant. Again, the cosine is 1 over the secant, whereas the secant is 1 over the cosine. And rounding out our reciprocal identities, we have the tangent and the cotangent. Once again, they are reciprocals, so we see our ratios here are flipped. And then for our reciprocal identities, the cotangent would then be 1 over the tangent of theta, whereas tangent would be 1 over the cotangent of theta. All right, we're going to go ahead and find the trig functions for our triangle. To begin with, though, we should state this is in fact a right triangle, otherwise we can't proceed and find the trig functions. If I want to start by finding my sine, we also need to know where we're starting. So I'm going to say our reference angle is down here at the bottom right. Otherwise, we might have the same ratios. For that angle, the sine is the opposite side over the hypotenuse, so it's going to be 9 over 15. If I want to take that ratio and help me find the cosecant, I would take the reciprocal, which would then be 15 over 9. For the cosine, I instead want to use the adjacent side, which is 12 over my hypotenuse of 15, which means for the secant, it would end up being 15 over 12. And then for my tangent function, it is the opposite side over the adjacent, which in this case is 9 over 12, which means my cotangent would have to be the reciprocal of 12 over 9. All right, guys, we're going to go ahead and find the 6 trig functions for this triangle. Again, we're going to iterate that we have a right triangle, otherwise we can't proceed. Also, we're missing a side here, but hopefully you remember your Pythagorean theorem, which states a squared plus b squared equals c squared. C is going to be our hypotenuse, b is going to be our bottom side, which means we are missing our a value. If I go ahead and plug things in, then we have a squared plus 4 equals 36. Subtracting 4 on both sides, we get a squared equals 32, which means a is the square root of 32. And if I simplify that, we get a equals to 4 radical 2. So I now know my missing side. Now that I have all of my sides, I can go ahead and find my functions. We'll go ahead and start with the sine again. And this time, we're going to go ahead and start with this top corner here. So the sine of that function is going to be 2 over 6. Which means that the cosecant of that same function would be 6 over 2, and I'll simplify that to be 3. If I look at the cosine, that's going to be 4 radical 2 over 6, which means that my secant would be 6 over 4 radical 2. And I'm not simplifying this, but I probably should to make it 2/3 or 3 over 2. And then last but not least, for my tangent, that is going to end up being 2 over 4 radical 2, which I'll simplify as 1 over 2 radical 2, which means that for my cotangent, it would end up being just 2 radical 2. And again, I probably should have simplified my other values here. I didn't have a lot of space, so I did not, but I would get 1/3 for the sine, 2 radical 2 over 3 for the cosine, and then 3 over 2 radical 2 for my secant. We're going to go ahead and solve for our triangle here. We know the sine of theta is 3 over 8. We also know that our reference angle is down here in the bottom right. So if I start there and I set up my sides, the sine is going to be the opposite side over the hypotenuse, which means I have 3 and I have an 8 there. To find our missing side, we're again going to use our Pythagorean theorem, which means I would have 9 plus b squared equals 64. If I subtract 9 on both sides, b squared is equal to 55, and then b is equal to the square root of 55, which we can't simplify. So go ahead and leave it like that. And now we have our three sides, we can go ahead and find the rest of our functions. Since we have the sine, we can already go ahead and use that to help us find the cosecant. We know it's a reciprocal, so it has to be 8 over 3. To find the cosine, we're going to take the adjacent side, which in this case is radical 55, and put that over your hypotenuse of 8. The secant is the reciprocal of that, which would be 8 over radical 55. For our tangent function, it's going to be the opposite side, which is 3 over radical 55. And then for your cotangent, it's going to be the reciprocal of our tangent, so it should be radical 55 over 3. All right, same idea here. We are given the cosecant of our angle, and we know that our angle is again the same spot, the bottom right corner. The cosecant is going to be the hypotenuse over the opposite side, which means that my hypotenuse is 17, my opposite side is 4. Again, we're going to go through our Pythagorean theorem to help us solve this for our missing side, which means we have 16 plus b squared is equal to 289. I'll subtract 16 on both sides to get 273, and then take the square root, and we get b is equal to the square root of 273. So I'll put that down here. And now, because we have our sides, we can go ahead and find our missing functions. All right, again, we're going to go ahead and begin with finding our sine function. Because we know what the cosecant is, that means the sine should be the reciprocal, which in this case is going to be 4 over 17. For our cosine, we're going to start with our adjacent side, which is radical 273. And we'll go ahead and put that over 17. For the secant, we'll take the reciprocal of that value. So we have 17 over radical 273. For our tangent function, it's going to be the opposite side over the adjacent side. And then last but not least, for our cotangent, it's going to be the reciprocal of our tangent. So we have radical 273 divided by 4, and then we have our 6 trig functions. All right, we have a word problem here. We're going to go ahead and try and solve for some missing information. We know we have a right triangle, so I'm going to go ahead and mark down my right angle. We have a hypotenuse of 15, and we have an angle of 42. The question is to find the other two angles and the other two sides. So I'm going to go ahead and label some things here. I'll call one side x, one side y, and we'll just call this z. The nice part about our missing angle is all three angles in a triangle add to be 180. And since I know that I have a right triangle, the other two angles have to be complementary. So to quickly find my z value, I could say that z equals 90 minus 42, which is then going to be 48 degrees. So I have found one of my missing angles. And now I'm going to try and identify x and y. To do that, I'm going to explicitly use 15 and 42 because those are the information given to me and there's no chance of error. If I somehow calculated this 48 incorrectly and I used it, then I would have an answer that's even farther off from what it should be. So to start off with, I want to find x. To find x, I need to identify the relationship between my angle, x, and 15. So for 42, x is my opposite side, and 15 is my hypotenuse, which means I would try and solve this using the sine function. So I can go ahead and set up my relationship as the sine of 42 is going to equal x over 15. And then to finish solving this, I would multiply 15 on both sides, which means I have 15 times the sine of 42 is going to equal x. Now to finish this problem, we're going to use our calculator. And it's very important you have it in degree mode because your angle is also in degrees. So if I type it into my calculator and I have the right mode, then for my answer, I end up getting 10.04. Okay, so I'm going to write that here under x. And then now we need to try and find our y value. It is tempting to go ahead and solve using your Pythagorean theorem, but because our x value was rounded, we can't really use it to find our y value. So for our y value, notice that we have the adjacent side to our angle and a hypotenuse, which means I'm going to start by using my cosine. So I have cosine of 42 is going to equal y over 15. Again, I multiply both sides by 15, so this time I have 15 times the cosine of 42 is equal to y. Again, we plug this into our calculator. You want to make sure you're in degree mode because your angle is in degrees. And I got an answer of 11.15 approximately. So I'm just going to go ahead and put that here. And one thing we can kind of do to double check here, my angle Z was 48 degrees, which is bigger than 42, which means the side opposite should also be bigger than the side opposite of 42 degrees. So since Z is bigger than 42, Y should be bigger than X, and that definitely happened, so I know at least that checks out. My answers are probably right. All right, here we have a surveyor who is standing 50 feet from the base of a large tree. He measures the angle of elevation to the top of the tree to be 71.5 degrees, so that's our angle here. And here's the 50 degrees he is from the tree. The question that we have is how tall is the tree? So we're looking for this distance here, which I'm going to go ahead and call h because it's the height of the tree. We're going to look at the relationship we have set up and decide if we should use sine, cosine, or tangent. Looking at our angle, we know that our h is our opposite. 50 is going to be the adjacent. So since we have opposite and adjacent, we're going to start by solving this with the tangent function. So I could say that the tangent of 71.5 is going to equal h over 50. I would then multiply both sides by 50. So we have 50 times the tangent of 71.5 equals h. If you go ahead and multiply that together in the calculator, again, making sure that you have your calculator in degree mode, then we get approximately 149.4 feet as our height of the tree. For our quotient identities, we have talked about this a little bit, but now we can state it. We know the tangent is always y over x or sine over cosine. And since these two are reciprocal functions, the cotangent is going to be the cosine over the sine, which is again the reciprocal of your tangent function. For our Pythagorean identities, our first identity says that sine squared plus cosine squared is equal to 1. And the reason why this works is this is related to our unit circle, where we know our radius of the circle is 1. And if we draw a triangle within that radius, we're going to have our sine and a cosine, and applying our Pythagorean theorem gives us exactly this formula. If I take each one of my terms, the sine squared, the cosine squared, and the 1, and I divide them all by cosine squared, I end up getting my second theorem, which is 1 plus tangent squared is equal to secant squared. And if I go back up to the original function and I divide them all by sine, I end up getting my last and final Pythagorean identity, which would be 1 plus cotangent squared is equal to cosecant squared. One of the nice things about these identities is anytime we see an expression or an equation with a squared trig function, we're automatically triggered to look at these three identities and to maybe use them or rewrite them to help us simplify or to solve what we're working with. When we're simplifying our trig expressions, we're going to try and use our quotient identities, our reciprocal identities, or our Pythagorean identities to fully simplify the expression into a single term. So right now I have two terms. I have tangent of theta and cosine of theta. I want to take them and rewrite them to get something to cancel so I no longer have two terms, but I have a single term. If we think about our quotient identities, I know that tangent is equal to sine of theta over cosine of theta. So I can rewrite it that way. And I'm multiplying by cosine of theta still. Now I can get my cosines to cancel out. And if I cancel out my cosines, then I'm left with just sine of theta, a single term. So I have simplified the original expression to be just sine of theta. For our second example, we have some squared terms. And I referenced earlier that anytime you have a squared trig function, you automatically want to think about your Pythagorean identities. So I'm going to do something on the side here. I have a cosine squared and have a secant squared. I'm going to write down the trig identity that uses cosine squared. So that is going to be sine squared plus cosine squared is equal to 1. And here I have 1 minus cosine squared. So the question is, how can I get 1 minus cosine squared from my original equation? And if I subtract cosine on both sides, then I would have sine squared is equal to 1 minus cosine squared. So now I can substitute sine squared in for my 1 minus cosine squared. So I'm going to go ahead and do that. And then I have secant squared. All right. My next step is I'm going to go ahead and rewrite secant using my reciprocal identities. So because secant and cosecant are reciprocals, I can rewrite it as 1 over cosine, but since it's secant squared, it's going to be 1 over cosine squared. If I go ahead and multiply those together, then I'm going to have sine squared over cosine squared. And if I again think to my quotient identity, I know that sine over cosine is tangent, which means that sine squared over cosine squared would then have to simplify to be tangent squared. And I have my final simplified expression. All right, for our next example, again, we have a squared trig function. So I'm going to go ahead and write down my expression, my Pythagorean identity that uses sine squared. And it was, again, sine squared plus cosine squared is equal to 1. Notice, though, I have 1 minus sine squared. So I'm going to have to move the sine squared over by subtracting it. And if I do, then we have cosine squared is equal to 1 minus sine squared. So now I can take my cosine squared and plug it in for my 1 minus sine squared, which gets me sine over cosine squared. From here, we want to try and eliminate the fraction term. So what I can do is I can rewrite this as sine over cosine times cosine. And I did that explicitly so that hopefully we notice sine over cosine. And we also notice 1 over cosine. Sine over cosine is going to simplify to be tangent. And 1 over cosine is going to simplify to be secant, using our quotient identities and our reciprocal identities. And while we might see that we have two terms here being multiplied together, we don't have a fraction, so this answer is preferred to the original expression. All right, so for our next expression, we're going to go ahead and try and simplify this again. I'm going to start by rewriting my tangent and my cosecant using the quotient identity and then the reciprocal identity. So for the tangent, I'm going to say that is sine of theta over cosine of theta times cosine of theta. And then for my cosecant, it is 1 over sine of theta. Okay, I can simplify the cosines. They're going to cross off. And then instead of dividing by 1 over sine, what I can do instead is I can multiply by the reciprocal, which would be sine over 1. And all I have to do is finish multiplying my two sine values together to get sine squared of theta. All right, for our trig identity problems when we're trying to solve equations, we're basically trying to make one side look exactly like the opposite side. So we're no longer trying to just fumble through and simplify as we go. We're trying to take one side and transform it into the other side. What's important here, though, is that we can only change one side. So we have to pick either the left side or the right side. Generally speaking, I try and start with what looks like the more complicated side because it's easier to work with when we're trying to transform it into the other side. All right, so for our first example here, we have tangent of theta times cosine of theta is equal to sine of theta. So again, we know these have to be equal. I'm going to go ahead and start with the left side because those terms look a little more complicated than just sine. So I'm going to transform my left side until I have simplified it to be exactly the sine of theta, and then I know that I'm done. For my tangent of theta, again, we're going to go ahead and rewrite that using our quotient identity. So I have sine of theta over cosine of theta, and I multiply that by cosine of theta. We're going to cancel out my cosines, so my left side simplifies to be sine, which is exactly what my right side is. I know that I'm done, and I know that I finished it correctly. Okay, here we have cotangent of theta times the secant of theta times the sine of theta equals 1. I am again going to start with my left side because it looks to be more complicated. I'm going to keep simplifying that until I can get it to be 1. To begin with, I'm going to write cotangent as the cosine of theta over the sine of theta. And then secant I can rewrite as 1 over the cosine of theta. And then I just have sine of theta to end with. Since all my terms are being multiplied, I can go ahead and cross-cancel my cosines. I can also cross-cancel my sines. And now I have simplified everything to be 1. And that's what I needed to be, so I know that I finished. All right, this one is a little bit more challenging. I do have a squared term, so I know sometime I'm going to have to use my Pythagorean theorems. But I did notice those two terms both have a sign in it. So I'm going to start by factoring out a sign. And if I do, then I have 1 plus cotangent squared of theta. And I'm hopefully going to set that equal to cosecant. If I go back to my Pythagorean theorems, 1 plus cotangent squared is going to equal cosecant squared. So I'm going to go ahead and write this as sine of theta times cosecant squared of theta. And now I can go ahead and rewrite cosecant as 1 over sine. So I have sine of theta times 1 over sine squared of theta. I can get my sine in my numerator to cross off with one of my sines in my denominator, so I am left with 1 over sine of theta. And if I rewrite that using my reciprocal identity, I have cosecant of theta, which is what I needed it to simplify to be. All right, for this example, we're going to go ahead and break up our fraction. So I'm going to start by writing it as secant over secant squared, and then plus tangent over secant squared. Our first term will simplify to be 1 over secant. And using our reciprocal identities, I can go ahead and simplify that to be cosine. For our next term, tangent is going to be the same as sine over cosine. And for secant, 1 over secant is the same as cosine. So in this case, 1 over secant squared is going to be the same as cosine squared. So I'm going to multiply by cosine squared. I can cancel out my denominator with one of my cosines in my numerator. And what I'm left with is plus sine times cosine. Now, since both my terms have a cosine in them, I can go ahead and factor that out. And if I do, we have cosine times 1 plus sine. And that is exactly what we needed it to be. All right, guys, that go ahead and completes our notes for this section. Good luck with the homework. Go ahead and get started.